if you go out in a curved space like this, nobody said that if you attach an additional frame when you return, that the frame still points in the same direction. So this is just the free-falling motion here, but you're probably thinking like you can feel that you go around here, and you're like a centrifugal force or something like this. We'll come to this. So anyway, we experimentally verify, and then we give it a blind and equation for you, which is a great for philosophers without further, and you transfer this guy. And then you can make an approach towards an answer to Laplace's question. You say, aha, Laplace wants to interpret this, which we interpret as acceleration of force. This is an equation is correct, because that it is numerically checked for very great precision if you neglect relativistic effect. So let's assume the real world is Newtonian. That's the name of the game at this level. And Laplace says if we change the equation, put an extra, and Laplace says, let's interpret this equation as an orthoparallel equation. Because that is the equation for a straight line. So take the x to the other side, and Laplace's question now takes the form. Laplace asks, is this of the form x double dot a alpha, or is alpha runs from alpha to right? Is this of the form x double dot alpha plus gamma, alpha, beta, gamma, at the points where you pass, x beta dot, x gamma dot, of t equals 0. That's the question. Is Newton's equation, is the gravitational force, can this be interpreted as an orthoparallel equation? No, it can't. Why? Because the gamma can only depend on the x where you are, but what about these two velocity factors here? This could only be interpreted as this for, well, not for zero velocity, but actually not really for any velocity, because if you have any velocity, you can have double the velocity, that's possible, and whatever choice you make for the gamma in terms of steps, you can't make this match. Because you can't get rid of the effect of the steps in the gamma, because the gamma only depends on x. So even if it depends on x step, it would be very difficult to get rid of the vectors here. So the point is, this simply doesn't have the form of the orthoparallel equation. That means one cannot choose for conclusion, one cannot find gammas such that the equation of this case of the gravitational force takes the form of an orthoparallel. In order to find such gammas, we need to be able to find the notion of straight line that could absorb the essentially using attributes to a force. Okay? It's done. You cannot also count this, not using the orthoparallel equation because you didn't have it. You spent several days thinking, and you realized there are other inconsistencies, which at the end of the day are this one. It is not possible. So the standard example from science is entirely wrong. Entirely wrong. You cannot curve space the way. Now, okay, we will learn something from our knowledge of the orthoparallel equation, from our understanding that it describes the direction. The gamma can be made any points, but only between 2 to 0. Yes. That's another problem. Yeah, but I would say that it can't include the specific points. Look, if I split this form, and then say it has a certain acceleration, I can make the acceleration vanish there by going to the coordinate system that falls with it. That's that. And now we say I can fall with it all the time. How do I make this all along the curve 0, then I have to walk like up here and jump down and let myself fall at this one, then I will fall together with the torque, okay? The problem is, the earth is round, and somebody at the North Pole makes this experiment and thinks of a coordinate system that's falling with him. He will be able to transform it with the gravitational force, apparently, whatever it is, and in this falling coordinate system, what at the same time someone makes the same experiment down here, so the system of the falling guy up here, this one will not be transformed away, this effect. So the homogeneous gravitational field, like we like it in the standard examples, can be transformed away entirely. I'll get to that later. But the inhomogeneous one can't. So that has to do with the question of how this can be transformed away. Okay, so this is rather sobering, but in fact, as so often, Laplace didn't look for it. So the full wisdom of the usual one takes us all the way to implement Laplace's idea in a way that works. And then Laplace asked, can we find a curvature of space such that particles move along straight lines? He didn't read Newton 1 properly. Newton 1 talked about a straight line. He talks about uniform motion along a straight line, not just motion along a straight line. Okay? So the full wisdom of Newton 1 is, use also the information from Newton's first law that particles have an influence of no force, and there's a uniformity. So if I course, in a two-dimensional flat space lane, this is uniform motion. These are equal amounts of time, one would say. That's a straight line, straight uniform line. This is also a straight line, but the motion described by this is not uniform because it gets slower and slower. Laplace, in this idea, only implemented this. Only tried to implement this. And that's often said in research proposals at the beginning. Okay. If you don't take things really seriously, you start and somehow you can't make this work, it won't make anything work. You have to take everything into account and then you start talking. The question is, rather than drawing these pictures and something that's very difficult to explain to students at first, is that a curve is more than the set of its points. A curve is the set of its points and its parameterization. It's a difference, right? So let's make it easier for students. Let's introduce the appropriate data structure to capture this. Introduce the appropriate setting to talk about the difference between these two. Difference. And that is something also known from school. To draw a space-time diagram. If you have a harmonic oscillator, you did this. How does the position depend on time? Let's do this for a one-dimensional world. Say this is a one-dimensional world here. And now I have a straight uniform motion. So this is a one-dimensional world like this, and I have a straight non-uniform motion. In the one-dimensional world, the motion is always straight, but the point is the difference between straight and uniform. Now, rather than showing this and remembering the parameterization, to attach a time axis, and we do not introduce new data, and we just represent the data in different fashion. If these were equal intervals of time, then it's clear how to translate these pictures. This one looks like slow, and so on. Because every time I write at this interval, it's like this for me. That's uniform straight motion in one dimension. But it's also straight motion in one dimension, but you can even imagine an extra dimension, it's still like the x-axis would be straight motion. And again, the time intervals would need you to have, hang on a second, equal time intervals, now we need to hang on, I'm confused. This is less time, that's the point. This is less time, which is not the same time, and this is now, looks like this. Exactly, goes up. I'm sorry, it's not getting slow. If it's getting slow, it's getting faster, of course. So I'm not confused. Are you also confused, though? Of course. Yeah. So this is getting slower, this is also getting slower, because the equal time it goes less. Relative is a rather embarrassing moment, okay? So we're trying to count off the zero, okay? Because I don't even have the excuse that relativity you can order the axis differently. You can have an excuse because the other axis step with it. So to the point, the insight is in space-time, if you attach time to space and a continuous entity, this guy here is simply, you can ignore the parameterization because nobody cares whether you now parameterize this curve in space-time in the most crazy manner. Because from every point where you are, you just look at this absolutely normal time it is. You no longer rely on the parameter that parameterizes the space-time curve because you store the information in the extra coordinates. You prove yourself from parameterizing the curve in a certain way because you store the information, but even better, in space-time, uniform and straight motion, where the uniform and straight must be set because you always think about time, and in space-time you don't think uniform and straight motion in space. In space-time, this uniform and straight motion in space is simply straight motion. No further questions asked. So, if you think Laplace's idea might work, if you only look at straight lines, if you only want to implement straight lines, then it will work in space-time, in Newtonian space-time. This has nothing to do with relativity. It's just drawing what you always do in school for the harmonic oscillator. It's not relativity. It's just representing the data you have in a different fashion. This goes one-to-one. Okay? But then we can use our ideas about straight motion. Otherwise, we have to use differential geometry that implements straight and uniform motion. It can be done too, but not in that way. Okay, so let's try this. So let's... Okay, and time moves. When 1 second elapses for that universal clock, then 1 second elapses for everyone else. Okay, regardless of their state of motion or their position or anything like that. Okay, so here's a person here, and they have a watch. And suppose that we strap a wristwatch to that baseball. Well, that wristwatch, as the baseball is moving, that wristwatch is ticking away time. Okay, so Newton's idea of universal time is that when 1 second elapses for that universal clock, that absolute clock, 1 second has elapsed for the universe. That means 1 second will have elapsed on this clock, and 1 second will have elapsed on that clock, regardless of the state of motion of this clock relative to that clock, and so on and so forth. Okay, so for Newton, space and time were both absolute. They were this sort of fixed things, these rigid things. Okay, but there's a certain problem with that. And Einstein came along, and he said, well, that's not quite right. That's not right at all. And these two ideas those two ideas about the space and time, they're wrong. Okay, and we're going to, in the process of these few lectures on relativity, we're going to discover exactly how they're wrong and in fact what is correct. Okay, so Einstein said that space and time themselves are not absolute, but they are relative. Okay, so basically that means that time, for example, time depends upon the motion of the observer. Okay, so here's an example. So you've got a watch, and I've got a watch. It's both very identical watches, and we synchronize them, and they're both reading exactly, say, 12 minutes. Okay, and then I go for, say, a walk around the building, and I come back. We put our watches next to each other again, and we find that, yes, they're in sync, they're both ticking at the same rate, but we will find that less time has elapsed for me. My clock is behind your clock. Okay, they were originally both reading exactly the same time, and ticking in sync with each other. I go around a walk around the clock, I come back, I find that they're both now ticking the same rate again, but my clock is behind. Less time has elapsed for me, okay, relative to your clock. Okay, so this is a fact about our universe, which we're going to try to understand. Okay, so basically, the first step in trying to understand how time and space are relative and what exactly that means is to explicitly show the motion of objects not only in space, like in this diagram, but also in time. Okay, so let me just write that down and I'll give you a diagram. So basically, any object, the key point here is that any object, regardless of its state of motion through space, is inexorably moving forward through time. Okay, so this object here, while it's not here, it's moving in space. Now it's not. Now it's just sitting there. It's not moving through space. And yet it's still moving through time. If I strap a wristwatch to that thing, time will be ticking for that object. Okay, even though I'm at rest, my clock is still ticking. I'm moving forward in time. Okay, so what we need to do is to show an object's motion not only through space, but also explicitly show its motion through time. Okay, and that's a space-time diagram. So let me give you an example here, a couple of examples. Okay, so let's suppose that this is Alice, and we're going to take the point of view here that Alice is at rest. It's not like me just standing here like this. Okay, and Alice has an x-axis, okay, so that's in, say, that direction to the right. And things can move along her x-axis back and forth. So let's draw her x-axis. So this is space according to Alice. So that's her x-axis, the x-axis according to Alice. We put a subscript A on it. That's space according to Alice. And things can be happening in this space. Okay, so for example, there could be, say, Bob. Bob is standing beside Alice at rest. So here's Alice, and here's Bob, standing at rest. Other things could be happening. Okay, if we have someone over here, say, Cleopatra, who is running with some CG, so running along Alice's x-axis, so in motion in Alice's space. Okay, or we could have people, other people, and so on and so forth. And so now this is showing their motion in space. This one is not in motion in Alice's space. This one is in motion in Alice's space. That's fine. But we also need to show the motion through time. Okay, so the simplest person for whom to show that is Alice herself. So Alice is at rest in her space, but she's moving forward in time. Her clock is ticking 1, 2, 3, 4. She's aging. Okay, so she's moving forward in time. How do you think we could represent that? Yeah. Vertical line. Perfect. Okay, so I'm going to take this diagram showing motion only in space and convert it into a space-time diagram. So there's the space part of the space-time diagram, and here's the time part, just a vertical line. Okay, so in this vertical line here, what we can say is this is Alice, right? This point here is Alice at this location, say x equals x, a equals 0. Say her position is 0 here. So this is Alice when her clock reads 0. Okay, this is Alice when her clock reads 1. This is Alice when her clock reads 2, 3, 4, and so on. Okay, so this is a picture, this is a space-time picture of Alice standing at rest. So as time goes on, her position in space doesn't change, it always remains 0, but her time nevertheless ticks away. Okay, so this is time according to Alice. And it will be time according to Bob and so on and so forth. This is Bob over here. Okay, so this is called the world line. This is a picture of Alice's trajectory through space-time. Now here is Bob. What is Bob? So Bob is standing some fixed distance away from Alice, like this. So the distance between Alice and Bob don't change. And Bob has his own clock. Tick, 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 tick. How would I draw Bob's world line in Alice's space-time? Yeah. Bob's not moving either, right? So whenever I split it, that's just draw a vertical line up to this. Right. So Bob initially is over here, some fixed distance away from Alice, maybe it's 2 meters. Okay, at a later time, he's also 2 meters. At a later time, he's also 2 meters, and so on. So he remains the same distance away from Alice as time goes on. Okay? What about Bob's clock? Okay? What about when 1 second elapses for Alice, say between here and here? How much time will it last for Bob? Are you sure? Yeah, so both the rest are respect each other. So that's basically, what if I put, I'll put a massive thing over there. That's a very strange over there. And let's put a dog. A massive dog and a dog out, that's looking over there. It will still true that 1 second lasts for Alice, 1 second lasts for Bob. Let me say yes. Let me say no. The correct answer is no. Okay? If you have a massive object over here, then that affects the rate at which time moves. So, as we heard yesterday, Sundance told us about that light beam. So remember, yeah, there's elevators here, and we have this light beam with bears like this. And he said, in order to make sense of this, this is the picture, in this accelerating spaceship, according to the equivalence principle, it means that if you were standing on the surface of the Earth like this, and turn on a flashlight, the beam goes out like that, the mass of the Earth will bend the beam in gravity against light. And since it has basically the same time moving there, it's moving there. And the speed will always be the speed of light. It means the time moves more slowly down here than it does up here. Okay, so time, the rate at which time moves depends upon your location in a gravitational field. So here's the Earth. It creates a gravitational field, actually the working of time in the neighborhood of the Earth here, such that time moves more quickly at this level than at this level. And you'll see a lot more of that as we go forward with these lectures. So it's not obvious that Bob's clock is going to be moving at the same rate as Alice's clock. But because there's no massive objects around, okay, it's reasonable to think that's the case. In fact, that is true. Okay, so what that means is when 1 second elapses for Alice, 1 second only lasts for Bob. But Bob's clock needs not be synchronized with Alice's. For example, when Alice's clock reads 0, Bob's clock might be 7. Okay, in which case, this is what? Or so on. Okay, so this is time according to Bob. The point is, when 1 second elapses for Alice, 1 second elapses for Bob. Consider our reference to each other. Okay, but now here we have Cleopatra. In a space diagram, her motion is she's moving with some velocity v to the right like this. Okay, so how would I draw her world line? Diagonal. Okay, so what that means is, as time goes on, Cleo is moving to the right. Okay, so her line is going to be tilted like this. Okay, right. And so now the question is, what is when 1 second elapses for Alice? Okay, how much time will it elapse for Cleo? Okay, so remember here, Cleo here has her own watch. Okay, this is on Cleo, and I've got a watch. My watch is ticking away. Okay, so Cleo's watch might read, say, 0 over there, and then as time goes on, it might read 1 over there, it might read 2 over there, and so on and so forth. Okay, so how do I, when 1 second elapses for Alice, how much time elapses for Cleo? More than 1? How many say more than 1? How many say less than 1? How many say same? Okay, so definitely not the same, and it turns out to be less than 1. Okay, so what it looks like is something like this. This is Cleo when her clock reads 0. Cleo when her clock reads 1 is actually maybe say over here. Okay, so that means as Cleo is moving like this, when her clock reads 1, she is at a certain location in Alice's space, and a certain amount of time has elapsed for Alice. Okay, so she's at a certain location in Cleo's space, and a certain amount of time has elapsed for Alice. Okay, and so more than 1 second will elapse for Alice. So maybe 1.5 seconds. So Alice will look at Cleo's watch and say, your watch is running slow. Okay, we'll look at this, and we will understand exactly why this slow down is on. Okay, and similarly, if this is 1 second for Cleo, we just march up in intervals like that. Okay, so what if we have, say, I don't know, Dogford, who's going really, really fast. Right, how do we draw his world line? More, right? So it's also tilted, but more tilted. Okay, so it might look something like this. So time according to Cleo, and we'll have time according to Dogford over here. Okay, so what about the spacing between Dogford, say 0? Where would I put 1 second? Would it be further up than this? Yeah, so the effect is more pronounced, okay, as we speed up. Okay, so now all of these motions that are happening are constant velocity. Bob is at a velocity, a constant velocity of 0 with respect to Alice. Cleo is at a constant velocity v with respect to Alice. So these are all uniform motion. What about non-uniform motion? What about accelerated motion? Okay, special relativity deals with accelerated motion. How do you say special relativity is fine with accelerated motion? How do you say special relativity is not fine with accelerated motion? Okay, so I hope to reverse this hands going up, okay? It turns out that special relativity has absolutely no problem with accelerated observers. And that's exactly how, in fact, Einstein, that was one of the stepping stones in getting from special relativity to general relativity and theory of gravity, is Einstein thought about accelerated observers in the context of